Good morning. Today we are going to study an ordinary differential equation which is entitled Cauchy-Euler ODE, the Cauchy-Euler differential equation. This is basically a detour from partial differential equations simply because this type of ODE appears in the process of solving other boundary value problems. So to an extent, this is kind of like a topic in 270, and in retrospect, probably I should include this topic when I teach Math 270, which is the class in ordinary differential equations. It's not typically a topic, but it's a simple application or extension of the second order linear ODE, which you are already familiar with. So we're going to go over this topic today, and then probably at the end of the lecture, or maybe on the next lecture, I'll go over the examples which lead to this equation. So once again, in this lecture, for a while, we're going to take a pause from PDEs and deal with learning another standard ODEs which appears in some applications. So let me remind you that you know already, or you used already in this class, the second order homogeneous linear ODE with constant coefficients. So recall that if you have a function of x, let's say y of little x, and a, b, and c are constant, second order linear ODE with constant coefficients will look like this: ay double prime plus by prime plus cy equals 0. And you have it in the formula sheet, but you might remember already the way to solve it is to set up the so-called characteristic equation. And then depending on the natures of the roots, you have basically several cases. You could have distinct real roots, in which case the solution is c1 e to the r1x plus c2 e to the r2x. You could have a double real root, and then the solution is c1 e to the rx plus c2 x e to the rx. And finally, you could have complex conjugate roots. So let's say r is alpha plus minus I beta, and then the solution is e to the alpha x c1 cosine of beta x plus c2 sine of beta x. In the course of the ordinary differential equations, you might remember that we use t instead of x typically, right? Because that usually denotes the time, the independent variable. So what we call a Cauchy-Euler equation is just basically a slightly more general equation of this type. So let's just state it right now. So as a definition, the Cauchy-Euler ODE is given by the following standard form: a x squared y double prime plus b x y prime plus cy equals 0. Okay, so it's a more general ODE than the previous one, because now the coefficients of the dependent variable are not constant, right? So again, y still denotes a function of x. A, b, c are still constant coefficients, but then you have extra terms here that depend on x. So notice there is some sort of association between the power of x in each term and the order of the derivative. So you can actually extend this definition to higher order ODEs. So y double prime has x squared multiplied by it, y prime is x to the power 1, and y by itself is just x to the 0 if you want, which is obviously 1. So you will see later which boundary value problems lead to this ODE. So for this moment, let's actually focus on how to solve it. And there's a very straightforward way to deal with it. With a clever substitution, we can reduce this to the previous type of equation with constant coefficients. I should mention here that the trick or the substitution that we're going to use only works if x is greater than 0. So that is a condition we're going to impose on this ODE. So we're looking for solutions for which the independent variable x is positive. Because the substitution that works in solving this is substitution is t equals natural log of x. And as you know, natural log is defined just for positive values of x. Okay, so how do we move basically with this substitution to solve this? The idea is to basically move on to an equation in terms of t, which hopefully is going to be easier to deal with. So let's do a chain rule here carefully. So if I take, if you differentiate y with respect to x, so if I consider y as a function of x, because I can treat t as a function of x, then we could use the chain rule and say dy dx is dy dt times dt dx. Okay, so instead of thinking of y directly as a function of x, you could think of y as a function of t first, which in turn is a function of x, which allows you to use the chain rule. And then notice that dt dx is going to be 1 over x, right? So the derivative of the natural log. Moving on, because we're going to need a second derivative as well. And remember, notice that in this little exercise with the chain rule, it's easier to actually use the dy dt, dy dx notation rather than the prime notation, which is kind of confusing in this context because y can be either a function of t or x. I mean, you can think of it as one of the two. So now we're going to take the second derivative, and notice that this time you need the chain rule, excuse me, the product rule as well. So first we differentiate with respect to x again, dy dt, again via the chain rule. So with respect to t again, so that's going to be the second derivative with respect to t, follow up with the chain rule, dt dx. So that's the derivative of dy dt. Keep the 1 over x as it is. And continue with the product rule, dy dt times the derivative with respect to x of 1 over x, which is, of course, minus 1 over x squared. By the way, if you don't like this little computation, you won't need it. I just want to prove how the solution is obtained for the Cauchy-Euler equation. But in practice, we're going to use directly the formula, which we will obtain shortly. So dt dx is 1 over x again. So let's simplify this a little bit. So d2y dt squared times 1 over x from dt dx times another 1 over x minus dy dt times 1 over x squared. So this is dy dx, and if we simplified second derivative with respect to x squared, let's pull up the 1 over x squared. So that gives me 1 over x squared d2y dt squared minus dy dt. Okay, so on the next page, we're going to plug in dy dx, d2 dy dx squared. So in other words, y prime. Now this, remember, this stands for y prime, this stands for y double prime, right, with respect to x. So we're going to plug in these quantities into the original Cauchy-Euler equation, and you will notice that because of this substitution, x will cancel, and that basically gives me, in the end, an ODE in terms of t, which was basically the goal in the first place. So with this substitution, we're going to change the ODE from an ODE in x to an ODE in t, right, y with respect to t. Okay, so on your notes, just pay attention to these three expressions, and let's just do now the substitution. I mean, in the Cauchy-Euler equation itself. So let's see, we have ax squared y double prime plus bxy prime plus cy equals 0. And now thinking of y as a function with respect to t, when we replace it into the equation here, we have ax squared y double prime, if you look at the previous page, is 1 over x squared times y double prime with respect to t minus y prime of t. And then the middle term is bx y prime, which previously can be written as dy dt times 1 over x, and of course plus c times y equals 0. So pause for a moment and notice that this substitution allows you to basically cancel x outside of the derivatives. Remember, y can be interpreted as either as a function of x, as it was from the beginning, or as a function of t via that substitution. Now, eventually, of course, the solution will be in terms of x, because don't forget that this is my original equation, right, in which y is a function of x. But because of that substitution, which I'm going to write it again here, t equals ln of x, right? So because of this substitution, you could think of y as a function of t. And when you do that substitution into the ODE, x will cancel. So let's actually, at this point, basically, you could replace y dy dt and this one by y prime or y double prime, meaning y double prime of t, y prime of t, right? So we could do this substitution over here. So with some rearrangement of the terms, we arrive basically to a second order ODE with constant coefficients and homogeneous, which we know how to solve. So a times y double prime minus y prime plus b y prime plus cy equals 0. And let's distribute this coefficient. Let's read that here. So a y double prime minus ay prime plus by prime plus cy equals 0. And then group this together, factor out. And this is something familiar to you, right? You have second order ODE with constant coefficients. Now, the thing to point out, and I'll emphasize that on the next page, notice that when you solve this, the characteristic equation is not going to be ar squared plus br plus c. It's going to be ar squared plus b minus a multiplied by r plus c. So you have to be careful to set up the characteristic equation carefully. Other than that, you solve this like any other second order ODE with constant coefficients. So, and if another step at the end is to make the substitution backward, right? From something in t to something in x. Because remember, this is for y as a function of t. So how do you solve it? Again, as I mentioned, you take the characteristic equation, you solve it, and then just like before, you're going to have three cases. You're going to have distinct real roots in which y is c1 e to the r1t plus c2 e to the r2t. But remember now, at this point, you have to go back to x, right? Because of that substitution. Remember, your answer in the end should be a function of x for the original equation. And if you replace t with natural log of x, you can make some simplification at this point, right? So remember, you can bring r inside the natural log. And cancel e with the natural log. So in the distinct real root case, the formula for the solution is given by c1 x1 to the r1 plus c2 x to the r2. And that's how you treat basically all the other cases. I'm going to just do them here, and then on the last page, I'll just basically write down the formula to have it in some corner as an example, and then I'm going to go over some examples on the same page. So case number 2, this actually appears a little bit less often. This one will appear quite often. You will see in the boundary value problems, which we will solve later. So let's say we have a double real root. C1 e to the rt plus C2 t to the rt. And again, we're going to make the substitution of natural log of x for t. Bring r inside, simplify the natural log with the exponential. So in this case, the solution would be C1 x to the r plus C2 natural log of x, x to the r. And let me see if I can squeeze the case number 3 here. We're going to write them again next on the next slide anyway. In the complex case, similar approach. Solution is e to the alpha t, C1 cosine of beta t, C2 sine of beta t. Replace t with natural log of x. Beta times ln of x, kind of messy here actually in this case, plus C2 sine beta ln of x. So anyway, just like before, e to the alpha x will be x to the alpha. I'm going to write it in a more compact form on the next page. But as I said, these are the 3 versions for the solution of the Cauchy-Euler equation. So in practice, as I said, you don't go over the proof. We just write this down to have in front of us whenever you need it. So you can write it on a formula sheet, and I usually provide it for exams, to have it in front of you. So what is the basic algorithm in solving the Cauchy-Euler equation? All right, so the starting point is to obviously make sure you recognize it as such, right? So the standard form of a Cauchy-Euler equation is a x squared y double prime plus bx y prime plus cy equals 0. Y is a function of x. And to solve it, you set up the characteristic equation first, which, pay attention, people always forget, I mean, not always, but often forget this. It's not going to be just like the one with constant coefficients. So the characteristic equation is ar squared plus b minus ar plus c equals 0. You're going to solve for r, and then you're going to have the 3 cases I mentioned before. Distinct roots. Solution is C1 x to the r1, C2 x to the r2. Case number 2, double real root. The solution is C1 x to the r plus C2 natural log of x, x to the r. And then the complex case, complex root, y is x to the alpha, C1 cosine of, inside of cosine is beta ln of x, plus C2 sine beta ln of x. Okay, so let's go over an example that leads to this, and then I'll see how much time is left because I don't want to overextend this. We're going to go over maybe quickly the type of boundary value problem that leads to this. So let's say I want to solve, let me see a quick example. Yeah, so let's say I want to solve x squared y double prime plus 5x y prime plus 4y equals 0. It is a Cauchy-Euler type. Okay, pay attention to the order of the derivative and the exponent to 2 x to the first y prime and then y by itself. So in this case, a is 1, b is 5, and b is 4. Okay, so the characteristic equation would be a r squared, that's 1 times r squared, plus b minus a, so it's 5 minus 1 r plus 4 equals 0. So r squared plus 4r plus 4 equals 0. We are in the double real root case, so that means r is minus 2. We are in the second case over here, so the solution would be c1 x to the minus 2 plus c2 natural log of x to the minus 2. Let's do another one. Let's say x squared y double prime plus 4 xy prime plus 2y equals 0. All right, what do we have here? Cauchy-Euler type, a equals 1, b equals 4, c equals 2. And characteristic equation is r squared plus 4 minus 1 r plus 2 equals 0. And this one has two distinct real roots because it can factor nicely into r plus 1 and r plus 2. So we have r1 equals minus 1, r2 equals minus 2. Therefore, the solution is c1 x to the minus 1 plus c2 x to the minus 2. So that being said, we're going to, I think I'm going to save it for next lecture so that I don't overrun this. So basically this completes all you need to go over homework, the next homework. There are two, I think, examples involving the Cauchy-Euler equation. But just to give you an overview of what you're going to do, this basically applies to a steady state temperature in a plate, in a circular plate or a portion of a circle, basically. For the Laplacian in that case in cylindrical coordinates, basically. So we're going to go over that example carefully. It's a steady state temperature in which we allow variation by two space dimension. Because notice that in most of these examples we're going to deal with, as I mentioned in class as well, we restrict ourselves to boundary value problems that involve only two variables. So if I want to solve a complete heat equation, one variable is time, the other one has to be a space variable. So I have a simplifying assumption to include only t and let's say the radius, right, in the spherical coordinates. Now, if I want to solve a steady state temperature and I want to still use two variables, I can go a little bit more general than that because I don't have the time variable. So remember, in the steady state temperature case, there is no time variable. So then I can essentially look at an object in which the heat depends on two space variables. But any simplifying assumptions will lead us to having basically only two variables. But more on that on the next lecture, and that's it for today.